Hello everyone. Welcome to my senior project presentation, which is hardware-accelerated breadboard AIs. This project is about building a complete CPU from scratch, using breadboards with basic circuit components and logic gates to optimize the CPU for a specific domain, which is machine learning. Before we get started, I'd like to thank my advisors, my internal advisor, Ms. Jefferson, and my external advisor, Mr. Patrick Lopresti, for advising me on this project, as well as Mr. Brady for coordinating and giving me feedback on this presentation. You might be wondering why I decided to pick up this project in the first place. As a field, AI has been propelled to the forefront of the public consciousness within the last 5 to 10 years, in large part due to the successes of neural network-based machine learning models, or ML models for short. And as a result, quite a few companies have started developing hardware specialized for ML models like neural networks, such as Google's tensor processing units, as you see here. I figured this would be an interesting aspect of the discipline to explore, and I've always been sort of curious to figure out how a CPU works down at the electrical level. So I set out to build the CPU from basic parts I could understand well, and get a taste for the kinds of challenges that ML hardware engineers were looking at, even though this isn't quite at production scale. Just to give you an idea of what I've roughly been working on, here's the roadmap of the project. I broke it down into 3 phases. The first phase is the construction of the base CPU components, where each component has its own individualized function and isn't yet interacting with the other components. Phase 2 is linking up all the components to form the baseline CPU, which includes building the control logic that manages each of the components, and here is also where we test the CPU as an integrated unit, after having modularly tested each of the individual components in the first phase. The last phase is the design of the ML operators unit, where I'm making the hardware to speed up neural network inference on the CPU and benchmarking the improvements. And I'll be talking more about that later. This was actually the original plan, but it's been more challenging than expected, of course, and I'm working through phase 3 right now. Getting into the meat of the project, I wanted to show you what sort of components make up the CPU. I've grouped these into 7 separate modules, the first of which is the clock. Also, you can see here the exact kinds of circuit elements I've used to build the CPU from. If you've taken some physics, you might be familiar with the capacitors, resistors, switches, etc. That you see on the boards. And the black chips running through the center are integrated circuits, or ICs, which are either logic gates that perform functions like logical OR, logical AND, things like that, or components that piece together a few logic gates for a slightly more complex function. This clock module synchronizes the steps of the CPU. When the green LED you see to the right of the board lights up, each of the components will carry out the next step they're instructed to. This next component is the ALU, which performs math functions like addition, subtraction, etc., as well as optionally some logical functions. On my CPU, I currently just have these 2 operations, addition and subtraction, but here is where the ML optimized components would go. This next set of components is a group of registers. Around the CPU, certain components need to store small amounts of important information that are accessible at any point in time, which the registers are handling. For example, the groupings of 8 chips on the left and in the middle, these are the A and B registers that store numbers that the ALU is going to process. Next up is component number 4, which is the memory. Memory is a fairly vital component, and we're going to need it for data storage. So this holds on to both our variables data, as well as the bytes representing our actual program instructions. So the large chips you see on the left, these are the actual data storage, and on the right side, these are registers that store the index that is currently being looked at in the memory. So getting near the end, 5 out of 7. This program counter, it simply stores the line number that the program is currently on, and it has a few functions to increment its value by 1, as well as jumping to some arbitrary line number. This here is the output register, which stores a single number like any other register, but it has a portion to convert the binary number it's storing into a more easily readable format onto these displays that you see on the right. And finally, we have the control logic, which is the heart of the CPU. The control logic processes the instructions we program into the memory, and it translates them into concrete electrical signals that are activating the specific CPU components. So I have some snapshots of the CPU along the timeline. The pacing was about a component each week, and the building process involved first learning the theory for the precise component functionality and the circuit construction, along with a building phase, followed by a testing and debugging cycle. By week 2, I had just a single board with a clock. After another 3 weeks, I had more than half the components done, or so I thought. So you see, the CPU architecture by week 5 was 8-bit, which means any number that I store or calculate in the CPU is limited to a max value of 255. For the construction of a CPU made from these common consumer-accessible circuit components, instead of the modern industrial-grade processor manufacturing pipelines, you would think that 8 bits would be good enough. But it turns out ML models are really just on another scale, and 8 bits just won't cut it. A lot of time I spent between week 5 to week 9 involved expanding each of the components to 16 bits, which was tight on time, since it's almost equivalent to rebuilding an entire extra copy of the 8-bit CPU. I would say that this was certainly the most challenging aspect of the project thus far. With it, though, I had space for about 65,000 16-bit parameters for my ML models. Here's the CPU in its current state, and I'm currently juggling debugging and ML operator design. I also wanted to show you some of the schematics I've made in the process of documenting my build, since I thought they looked pretty cool. Here are 2 of the examples of schematics that I've made. On the left here, this is one of the 3 submodules within the clock module. Much of the theory work was about understanding the dynamics of the components that I used and being able to replicate them from simpler components, which drawing the schematics helped me to do. Within the purplish, pinkish looking box labeled 555, which is one of the integrated circuits, you can kind of break it down into these 6 circuit elements like I've done here. Being able to decompose components like this was pretty important for understanding the CPU well enough to debug it when things didn't happen according to plan. Sometimes you also get certain constructions that pop up in many different aspects of the CPU, for which the archetypal example is the D flip-flop that you see on the right. The D flip-flop stores a single bit of data and can be constructed from 5 logic gates, 1 capacitor, and 1 resistor, as shown. This comes up everywhere you need to hold on to data, like in the RAM and the registers. So I wanted to give a bit of insight into how the CPU actually uses these components to run a basic program before we head to the ML section in a moment. Consider this phase 2 with the control logic. So hopefully with this, you can see the basis from which we can generalize and implement an ML model, which involves a similar kind of computation and data storage flow in this sample program. So what I have on the screen are the abstracted representations of some of the components you've just seen, in particular the registers and the memory for data storage. And we're going to be taking a look at some of the foundational operations, which are taking 2 numbers, adding them, and moving them to the output register to be displayed. So recall that under this CPU architecture, the registers are storing single numbers that are needed on hand at any time by other components, and the memory stores a long list of either variables or program instructions in a section at the top, and the variables usually come after. This program involves 4 assembly instructions which load our 2 add-ins into the registers. They compute and store the result, and then they're sending the result into the output. So if you have some software familiarity, you might know assembly as a very low-level representation of the CPU instructions. We're taking it from a bit of a new perspective from the hardware level, so you might be surprised to hear that from this standpoint, assembly is actually fairly high level, being composed of multiple steps of control signals that are activating each of our components. Below are 4 instructions. We've stored the 2 add-ins at index 4 and 5. For simplicity, I've chosen 1 and 2 as the add-ins. On the left, we have the status of each of the registers, and again, A and B are the 2 add-ins that the ALU will add, and the output register is what we're going to see on the display. So first, we're going to load A. So there's a 4 after the load A, which indicates the index of the number we want to load. So we go to index 4 and see the value 1, circled in red. Load A passes this value from memory to the A register. So now the A register is holding the value 1. Behind the scenes, the program counter increments to the next line, and the control logic processes the next assembly instruction into specific control signals. Load B is the next instruction, and it works similarly to load A, except B is receiving the new value. So at index 5, we have the value 2, and it gets loaded into the B register. Program counter ticks, and we see the next instruction, add 6. Add 6 adds the values stored in the A and B registers, and it stores it in the index in memory that we ask it to, which is 6 in this case. After the step, we now have a 3 at index 6. Counter ticks, we're on the last instruction, out 6. This simply feeds the value at index 6 to the output register. And that's it. We've successfully tricked a bunch of electrical signals through silicon and copper in order to see these nice numbers on our display. So what's so great about adding 1 and 2, you ask? This is just the tip of the iceberg. Of course, we won't just be adding 2 single-digit numbers in our ML model, but instead thousands of operations composed from more basic operations like addition. So the great thing about having a CPU is that it just takes a bit more time to run through all the computations. And as long as we can get it done quickly, the rest of the work is just down to programming. So here is perhaps the most interesting phase of the project, and I want to take a moment to talk about the machine learning phase. I mentioned earlier in the presentation that I haven't quite completed this section. However, it's been necessary for me to plan out this section carefully, and I believe this phase will proceed roughly according to the plan. So I can share with you what I've got in store. I'm running a little over the bounds of the senior project timeline, I know, but hopefully that means on my own time I can make something a little more advanced than what I currently have. I believe I mentioned the type of model I'll be using in the introduction, which is a neural network. Neural nets are fairly computationally heavy, but they tend to have strong performance, supposing you have the computational power necessary. And the task I'm going to be training the model on is a fairly simple task called MNIST, which is handwritten digit classification. You have these images where people have drawn a number, and the task of the model is to try to output the number that is represented. And this is actually a bit of a harder task than it seems, because the model only sees a bunch of pixel values. There are a bunch of zeros in the background and ones where the number is. And the model doesn't get to see the image like we do. A machine learning model doesn't understand the image idea like a human. It just sees a bunch of values, and its task is to look at this bunch of values and predict what number is being represented. But with that said, for a neural net, it's a fairly simple task, and I wanted to choose this task because I actually don't have that many parameters available. I've got 65,000, which for a machine learning model like a neural network, it isn't necessarily that much. So I wanted to pick something simple and something that's reasonable to compute, which isn't taking something like 10 years, 10 years to run the model. Regarding the operators in the model, one of the reasons I chose a neural network is because a neural net is basically comprised of 2 operations, roughly speaking. On the top you have matrix multiplication, which is simple. It's made up of just addition and multiplication, but you have to do this a lot of times, which means it's computationally intensive. On the other hand, on the bottom, the other operation is an activation function. As an example, this particular choice of activation function you see here is a sigmoid, which is 1 over 1 plus e to the negative x. The important thing to focus on here is the e to the negative x, which is an exponent, right? This sort of thing, especially if you're using a decimal exponent instead of an integer, isn't so simple as just addition and multiplication. With that said, we don't have to do this operation that many times. So this is kind of like the opposite, where it's a complex function, but it doesn't take as much time. So I thought it would be an interesting thing to try to see how we could optimize both of these functions and see just how much faster we could get a neural network to run. The name of the game is really just optimization. It's benchmarking. I'm going to run the model with just the baseline CPU and see how fast it is. And then using various versions of operators I'm going to implement in the hardware, I'll try to see how much faster I can get each of these versions over the baseline version. And we'll see whether that's significant or not. And again, this is the component that I haven't quite completed yet. And so on that, I'll be trying to finish, or at least make good progress on this in the next few weeks. So that's it. Thank you for coming to my senior project presentation. I hope this was interesting or that I was able to teach you something new. And to anyone interested in software or just computers, I highly recommend looking into the hardware side of things and doing some electronics projects on your own. This was a really fun sort of project for me, and I learned a lot both from the hardware and electronics theory standpoint and on the engineering and project logistics aspect. Yeah, and I believe we're moving into Q&A if we've got time.